everybody. So in this video, I am going to explain about concepts of solutions. That means most important synopsis of solutions topic. So lesson structure. Here we'll discuss about solution, concentration terms. Next, positive and negative deviation from Raoult's law. Ideal solutions, non-ideal solutions. Next, colligative properties, relative lowering of vapor pressure, depression in freezing point, elevation in boiling point, ebullioscopic constant, cryoscopic constant, Van Hoff factor, and osmotic pressure also. Next, see here, what is the solution? So, solution or it can be also known as a true solution. True solution. So, it is homogeneous mixture of two or more components. So to form a solution, there should be minimum of two components. The component which is present in large quantity is solvent generally, and the other component is known as solute. So major component is solvent, minor component is solute. So here example is given, sugar solution. In this solvent is water and solute is sugar. Next, methods of expressing concentration terms. That means methods of expressing concentration of a given solution. So most important one, molarity, denoted with capital M. It is the number of moles of solute present in 1 liter of solution. So final formula we can write like this. Capital M, molarity equal to given weight of solute in grams by gram molecular weight of solute into 1000 by volume of solution in ml. So this is final formula. Next, units of molarity, moles per liter or simply molar. Moles per here liter power -1 should be there. Liter power -1, or we can say molar. Molar capital M. So very important. Next, molality. Molality denoted with small m. It is the number of moles of solute present in 1 kg of, that means 1000 grams. 1000 grams. 1 kg of solute. That means number of moles of solute present in 1 kg of solvent. 1 kg of solvent. So here 1 liter of solution, definite quantity in case of molarity. Here 1 kg of solvent is definite quantity in case of molality. So I will write final formula for this. Molarity equal to given weight of solute in grams by gram molecular weight of solute. This is common, into 1000 by weight of solvent in grams. This is final formula. Next, units, moles per kg, or we can say molal, which is small m. So molarity and molality both are important. Next, mole fraction. Mole fraction denoted with chi or x. Mole fraction, Greek alphabet chi, or more conveniently we can take x. So it is the ratio of number of moles of one component and number of moles of all the components of solution. The mole fraction, number of moles of solute by total number of moles of solution. or you can say number of moles of solute by total number of moles of solution is mole fraction of solute. Similarly, mole fraction of solvent is number of moles of solvent by total number of moles of solution. So, mole fraction of solute and mole fraction of solvent will be equal to 1, unity condition. That means sum of mole fractions of all the components of solution will be equal to 1. Next, mass percentage or weight percentage. So, it is denoted with percentage W by W. So, mass percentage is the mass of component per 100 grams of solution. That means you can write mass percentage equal to mass of solute by mass of total solution into 100 is mass percentage. Next, ppm, parts per million. Number of parts of component by total number of parts of all the component into 10 power 6. So 10 power 6 is million here. Next. So here I will write one more relation. Relation between molarity and molality. Molarity equal to 1000 into molarity by 1000 into density minus molarity into molecular weight of solute. This is a relation between molality and molarity. Remember this relation. Next, one more. Mole fraction and molality. Mole fraction of solute equal to molality by m plus 55.5. And the mole fraction of solvent equal to 1 minus mole fraction of solute. Remember this formula. Next, Raoult's law. At a given temperature, the relative lowering of vapor pressure of dilute solution containing non-volatile solute is equal to mole fraction of solute. Very, very important. That means simply you can write relative lowering of vapor pressure or LVP. Delta P by P naught equal to mole fraction of solute. So very, very important formula. Mole fraction of solute. This is Raoult's law in case of non-volatile solute in volatile solvent. Here we can write like this, delta P by P naught. Next, Henry's law. So Henry's law states that at a given temperature, partial pressure of gas in vapor phase directly proportional to mole fraction of that gas in solution. That is P of gas directly proportional to mole fraction of gas or pressure of gas equal to Kh into mole fraction of gas. So Kh is Henry's law constant. Henry's law constant. Very, very important. Next, osmotic pressure. The pressure which is to be applied on solution side in order to stop osmosis. Osmosis. MO should be there. Osmosis is known as osmotic pressure. So which is denoted with pi. Denoted with pi. Osmotic pressure. So what are isotonic solutions? The solutions which are having same osmotic pressure at a given temperature. isotonic solutions or isoosmotic solutions. So for isotonic solutions, if you take two solutions, pi 1 equal to pi 2, two solutions are said to be isotonic if they are having same osmotic pressure, or we can say C1 equal to C2. Concentrations must be equal. That is N1 by V1, N2 by V2. Or N1 means we can write again weight by molecular weight, W2 by M2 V2. So this is nothing but isotonic condition. Very, very important for calculation. Isotonic condition. Pi 1 equal to pi 2, C1 equal to C2, that implies N1 by V1 equal to N2 by V2. So N is number of moles, V volume, W weight, capital M molecular weight. Next, yes, selene. That means NaCl is isotonic with blood. Remember example. That means both are having same osmotic pressure at a given temperature. Next, positive deviation from Raoult's law. So very, very important. Vapor pressure of non-ideal solution is higher than that of predicted value by Raoult's law. So here properties, characteristics, positive deviation. So PA, so here P total can be P naught A XA plus P naught B XP, or PT equal to PA plus PB. Remember this. If it is equal, ideal condition. This is ideal condition. That is Raoult's law. Ideal solution or ideal condition. If this condition is satisfied, then the solution will be ideal solution, Raoult's law. RAOULP. Very, very important. If it is greater than, see here, PA greater than P naught A XA, PB greater than P naught B XB, positive deviation. Delta H mixing, positive. Delta V mixing, positive. Examples, ethyl alcohol, water, acetone and carbon disulfide. Similarly, negative deviation. Negative deviation means vapor pressure of non-ideal solution is lower than that of the predicted value by Raoult's law. So here all are negative. PA less than P naught A XA, PB less than P naught B XP, delta H mixing less than 0 negative, delta V mixing less than 0 negative. Examples, HNO2, not HNO2, HNO3. HNO3 and water. Here we must take 68% of HNO3. Next, chloroform and acetone. So these mixers can show negative deviation. Next, ideal solution. It obeys Raoult's law at all conditions of concentration and temperature. So delta H mixing 0, delta V mixing 0. So benzene, toluene and N-hexane, N-heptane. So clearly remember like this. For ideal solution, P total equal to P naught A XA plus P naught B XP, or PT equal to Pa plus Pb. This is ideal. Next, non-ideal solution, which is showing positive deviation. Remember like this. Positive means Pt greater than P naught A XA plus P naught B XB, or Pa greater than P naught A XA and Pb greater than P naught B XB. Next, similarly, non-ideal solution, which is showing negative deviation. P total less than P naught A XA plus P naught B XB, or Pa less than P naught A XA and Pb less than P naught B XB. Remember like this, all conditions. Very, very important. Ideal, non-ideal, positive, non-ideal, negative deviation. So these are liquid and liquid type of solutions. Ideal and non-ideal. Next. So these are colligative properties. Colligative properties. Colligative properties. Here there are 4 colligative properties. So first one, relative lowering of vapor pressure. Next, elevation in boiling point, depression in freezing point, and osmotic pressure. These are 4 colligative properties. Relative lowering of vapor pressure, elevation in boiling point, depression in freezing point, and osmotic pressure. These are colligative properties. So first, relative lowering of vapor pressure. The ratio of lowering of vapor pressure to vapor pressure of pure solvent is known as relative lowering of vapor pressure. So this is RLVP, relative lowering of vapor pressure, which is Raoult's law. Next, according to Raoult's law, here it is given. The relative lowering of vapor pressure of dilute solution containing non-volatile solute is equal to mole fraction of solute. Here X2 is mole fraction of solute. So where N1, N2 are number of moles of solvent and solute. So take 1 as solvent, 2 as solute. Depression in freezing point of a solution. So depression means the decrease in freezing point of solution when non-volatile solute is added is depression. Depression means decrease. So a delta TF equal to Kf into molality. Kf into molality. So molality can be written as Kf into weight of solute by, say, molecular weight of solute into 1000 by weight of solvent, W1. So M is molecular weight of solute, or you can take it as M2 also, M2. Next, Kf is molal depression constant or cryoscopic constant. So it can be calculated Kf equal to RTF square by 1000 into LF. So it is characteristic property of only solvent. Kf depends on solvent only, or Again, LF equal to delta HF by enthalpy of fusion by molecular weight of solvent. So Kf is the property of solvent only, or Tf square by 1000 into Lf. Lf equal to delta HF by molecular weight of solvent. R is gas constant, Tf is freezing point of solvent, Lf latent heat of fusion of solvent. Delta HF is change in enthalpy of fusion of solvent. Capital M is molecular weight of solvent. So from this you can calculate Kf. Next. Elevation in boiling point. Elevation. Increase in boiling point of solvent when non-volatile solute is added. So delta Tb. So delta Tb equal to Kb into molality. So where Kb into molality can be written as W2 by M2 or M 1000 by W1. So M2 is molecular weight of solute. M2 or M you can take. Next, Kb is molar elevation constant or ebullioscopic constant. It can be calculated by using RTB square by 1000 into LV, and LV is delta HV by molecular weight of solvent. Kb also depends on solvent. So depends on solvent only. Characteristic property of solvent. So R is gas constant, Tb is boiling point of solvent, LV latent heat of vaporization of solvent, delta HV change in enthalpy of vaporization of solvent, M is molecular weight of solvent. So molecular weight of unknown solute M, or we can take it as M2 also, M2. So in this slide also molecular weight of solvent, here M or M2. So take 2 for solute, 1 for solvent. So cryoscopic constant and ebullioscopic constants here. Ebullioscopic constant can be defined as here. Elevation in boiling point produced when 1 mole of non-volatile solute is dissolved in 1 kg of solvent. It is denoted with Kb and units Kelvin into kg mole inverse. Similarly, cryoscopic constant Kf. The depression in freezing point produced when 1 mole of non-volatile solute is dissolved in 1 kg of solvent. So here also same units, Kelvin kg mole inverse. Mole inverse. Kb and Kf are having same units. Next, Van't Hoff factor. Van't Hoff factor, let I, equal to experimental colligative property, or we can take it as abnormal colligative property by normal colligative property, or normal molecular weight of solute by abnormal molecular weight of solute, or we can say number of particles of the number of particles after dissociation or association of solute divided by number of particles before dissociation or association of solute. So if I value greater than 1, there is dissociation of solute. If I value less than 1, there is association of solute. If I value equal to 1, no association or dissociation. Dissociation or association. So Van der Waals factor is applied when solute undergoes dissociation or association in solution. Van der Waals factor I. Small I should be there here. Small I. So here abnormal means observed or experimental. Abnormal can be taken as experimental or observed. Normal colligative property theoretical or calculated. So any colligative property, right here, any colligative property inversely proportional to molecular weight of solute. Very, very important. So this is about synopsis of solutions and colligative properties. So in next video, I will explain one more topic. All the best and thank you.